we go on to our second talk in this session, which will be held by Sepideh, I hope I spell it right, pronounce it right, Hatamikia. She's, she is, sorry, PhD from the Medical University in Vienna, currently working at she's the head of the computational imaging and medical image analysis and artificial intelligence group in Krems, Danube Private University. And you will tell us something about revolutionizing radiology. So I'm looking forward to your speech. The floor is yours.
Thank you very much, Susanne, for a kind introduction. As introduced by my colleague, I'm Sepideh Hatamikia. I'm an assistant professor at Danube Private University and head of computational imaging in MII research group. In addition, I'm a researcher in Austrian Center for Medical Innovation and Technology since 8 years. The topic of my talk today is about revolutionizing radiology, basically exploring the synergy of data science and artificial intelligence in future of medical imaging. The healthcare industry normally generates a vast amount of data. This is what we call big data. Using data science and analytics, we can extract meaningful insight from the wealth of this information. Basically, we can extract knowledge from this data. This can bring us enormous potential. For example, we can identify high-risk patients. We can optimize resource allocation. We can enhance prevention care strategies. We can optimize treatment planning. We can actually have more efficient decision-making and treatment outcome. Medical imaging technologies such as magnetic resonance imaging, computed tomography, mammography, ultrasound, and many more actually play a crucial role for clinicians to provide comprehensive visual information about the human body. They can generate a large amount of data about myocardial disease, about abdominal illnesses, cancer of different tissues, neurological disorders, and other important and serious health problems. However, this data and this basically information needs to be interpreted and analyzed efficiently, and that's exactly where artificial intelligence comes to the scene. AI has revolutionized medical diagnosis because it can provide higher accuracy, higher precision, and higher speed. Image analysis by AI actually has shown superior performance compared to traditional methods. Large data sets can be processed and analyzed using AI to extract hidden and complex information within the medical imaging data, those information which cannot be seen by human eyes, basically. So AI has shown that it can not only do several tasks of radiologists instead of them, like automizing their tasks, but can also do several tasks that radiologists cannot do, basically speaking. For example, it can predict heart attack from a single X-ray, or it can predict Alzheimer. It can predict heart-to-see fraction for musculoskeletal injuries. It can identify patients at high risk of thoracic complication, and it can also predict the surgery outcome. This is one of the main arts of artificial intelligence data science in the field of medical imaging, because basically clinicians cannot do that. They cannot just get simply these outputs. By applying big data, radiological procedure in radiology department has boosted a lot. However, we need a lot of infrastructure. For example, we need robust connection. We need cloud to store the data. We need cyber. We need community to transfer data between different departments and so on. But once we have all this infrastructure and data in place, then AI-enabled, AI-powered medical image analysis can basically be applied, which opens a new floor for innovation in medical technology. It can support all imaging chain, starting from decision support, examination, which is data acquisition, reconstruction, which is data generation, post-processing, diagnosing, and prognosis. I'm going to give you some practical example about the application of data science and AI in cancer. Basically, we could detect cancer in very early stages. It can actually help us for timely intervention. It can help us to save lives and improve patient outcome. So here you see two examples of mammogram from a woman, which was taken, for example, in the timeline 1 year between. Here in this figure, you see that the patient came with a very small lesion, the one inside the red rectangle. It could not be detected by a specialist, by a radiologist, because it's so small, it's not very much easy to detect that one. But then the patient comes after a while, just think of a year, with a big lesion. And when radiologists look at the same location, they see, oh wow, there was something we missed it, because it's so small, because it's not easy to detect it. But this is dangerous, because then it prevents treatment at the correct time, right? So recently, AI has shown that it can predict breast cancer up to 5 years in advance. This is super helpful because you could know what is going to be happening to you. Therefore, you can prevent it, or you can diagnose it in time, and you can treat it in a timely manner. Another application of data science, AI, and image analysis is for automatic tumor segmentation, which is a very important task of radiologists. Normally, manual segmentation is done, which means that radiologists sit and basically delineate the tumor, right? This is the gold standard as done routinely in the clinic. However, this process is very time-consuming, and also it suffers from inter observer variability, meaning that when two radiologists do the segmentation on the same tumor, or when one radiologist does it again after 6 months, there are differences in the segmentation results, which would influence the whole analysis pipeline. It's not ideal for us. Therefore, here, AI-based automatic segmentation can happen, which can help standardizing the segmentation result to have more consistent and even higher precision. So here in the left side, you see a segmentation which was done manually by a radiologist. In the right side, you see one which was done by a computer. Can you maybe see the difference here? Almost identical, I would say. So this is one of the biggest art of AI here. Another application of AI, which is very much attractive, is in the predictive modeling. AI has shown great promise in predicting the treatment outcome in advance, meaning that we would know what we would get from the treatment in advance, right? So it can be very much helpful because it can reduce unnecessary intervention, it can reduce healthcare costs, and also risk to the patient. This is one big step toward personalized medicine because the treatment plans are considering individual variation in anatomy, in physiology, and disease characteristics. I give you some example. Neoadjuvant chemotherapy is one of the common approaches which is normally given to a patient with ovarian and breast cancer. However, prediction of response to neoadjuvant chemotherapy is very challenging because the clinician cannot guess. They normally give it to everyone, but they don't know. There are patients who do not benefit from this treatment, but they cannot guess it in advance, right? So what is actually happening right now, we actually analyze medical imaging data from those patients. For example, we analyze MRI from breast or CT from ovaries, and then we apply AI prediction models to these imaging data, and basically we can say that patient number 1 is basically benefiting from the chemotherapy, patient number 2 doesn't, and patient number 3 actually benefits, and so on. This is super helpful because we could exclude those patients who would not benefit from chemotherapy in advance. Chemotherapy has toxicity effect, right? And also the patient is already kind of very weak because of the sickness, because of the cancer. So if we know if the patient is not benefiting, we should exclude it from the beginning. And this is one of the applications of AI here. Radiomics is one of the promising methods in the field of cancer. Radiomics is defined as extraction of information from medical image data using advanced feature analysis algorithms. Radiomics features are quantitative features. Radiomics features are quantitative imaging features or biomarkers which actually can identify hidden and complex patterns with imaging data, those that you don't see by eyes. And they normally are extracted from a segmented image, a tumor, lesion, or whatever segmentation, and they describe the shape of the lesion, the intensity, the texture, basically its voxel arrangement, and they have shown great promise. In a study which was done by me and my colleague and my group, basically we could apply radiomics and combine it with artificial intelligence for prediction of response to chemotherapy. And for 2 different types of cancer types, we got an accuracy up to 95%, which is very promising, I would say. In another study, we did a comprehensive literature review where basically image analysis helped for ovarian cancer patients. As you see here, well, we realized that radiomics has shown great promise for decision making support. But what was the interesting part of output of this study was that multi-omics integration could outperform single data type analysis, meaning that when imaging data was combined with other type of data, as you see here, so many different ones, like serum markers, genomics, proteomics, transcriptomics, and so on, the performance was much higher. This is one of the big and I would say high topics of data science, to integrate different data types, therefore enriching the information space and getting and improving basically the performance of the AI model. Data science and AI is also used for image reconstruction. Image reconstruction is basically the process of generating a 3D image out of 2-dimensional images. Normally, when you want to take a CT, you take the patient to the CT room, and then you have a 3D image. However, recently, we have the invention of cone-beam CT devices. Here is one C-arm. C-arm is a cone-beam CT device. It's called C-arm because it's like a C and this attached arm, and it can basically do a 3D imaging within the surgery room. So this is a portable CT. We bring it in the CT room, and we can take a 3D image intraoperatively, which is very much beneficial. It gives a 3D view to the surgeon during the surgery, exactly. However, the problem with this technology is that it requires a lot of 2-dimensional images to create a 3D image. This would introduce large amount of radiation dose to the patient, which is not ideal, of course. So data science and AI has shown that it can decrease the number of needed projection, therefore it can decrease significantly the amount of radiation dose to the patient, which is a big advantages of applying this AI and data science in this field. In addition, here is another, let me just show you. This is a robotic cone-beam CT device. This was done with a colleague, with a project with our colleague in Heidelberg. So we acquire data using that. It's just rotating, acquiring 2-dimensional images, and we want to create a 3D image. However, again, the problem is that using advanced image reconstruction algorithms that are nowadays used, it's very time-consuming to do it because they are computationally very expensive. They are so time-consuming, and they do not allow the real-time setup, real-time 3D generation if we want a high image quality. Again, AI and data science here help to have much faster reconstruction, therefore enable real-time imaging with the high quality within the surgery room. So another advantages of the data science and AI is to generate synthetic images. So here, if you see, in a collaboration with our partner, we could generate some synthetic data from XCAD Phantom, and this data is very much similar to patient CT data, as you see. What's the advantages? So medical image analysis using neural network has this problem that it needs a big amount of training data. However, especially in the medical field, we do not have that much patient data, or it's hard at least to collect it, right? So synthetic data would bypass this problem because it can allow us to generate unlimited sample size with unlimited annotation. Therefore, this is very much important and active research area to generate synthetic images. In addition, AI and data mining is very much helpful in interventional radiology. For example, for fusion of 3D image to 2D image. Normally, in interventional radiology, we have 3D prior image, which is an image which is taken from the patient past, like 1 month ago before the surgery, 2 weeks before the surgery. Like CT, like MRI, 3D image is available. However, during the surgery, not always we can have access to 3D imaging, and it's ideal to not actually have a lot of those, but get just like a few 2D images. So the art of AI here is to combine these basically prior 3D image with the intraoperative 2D image and give a 3D view to the surgeon. So we take 2D image, but we give a 3D view to the surgeon. This is very much helpful, I would say. Here is an example in the traumatic patient, and the next one is an example, again, 3D image, 2D image during intervention, and 3D view during intervention while we only take 2D images. And this is in a case of prostate arterial immobilization patient. Another application of AI and data mining is in creation of virtual angioscopy. Basically, it's a very helpful planning tool for surgeons to practice before the intervention or surgery. Here, this is a case of endovascular navigation. So we have a 3D prior image. We can generate a 3D rendering of aorta. Then we can, using AI, we can generate a virtual arthroscopy, which helps the surgeon to have a 3D imagination before the surgery comes. So they are ready to do the surgery because they know the anatomy of that specific patient, and they get trained before the surgery to do it in the most efficient way. And finally, AI is used in robotic application for catheterization lab, which is an angiography suite. And this is a place where radiologists do a lot of image-guided procedure by combining images, by combining biosignals, by combining blood results, and AI and data mining is applying to support their decision-making. Basically, this robotic catheterization takes the physician away from radiation spell. Why? Because normally, if this is the surgery, using this kind of robot surgeon, here we have the human remote operator, which is sitting outside of the surgery room, not within the surgery room. Therefore, we take it away from the radiation dose. Because here we have, as you see here, we have the imaging device which gives radiation dose, but the surgeon is sitting outside. And it also helps to have more precise treatment because it's robotically done. Although this is a very nice actually approach, but it needs a lot of computational infrastructure. It needs powerful augmented reality for real-time view. It needs AI-based analysis to do analysis at the same time. A lot of data are available. It needs a good internet connection and so many other infrastructure. So to wrap up, data science and big data actually has the potential to personalize the medicine. It can help in efficient management. It can provide more innovative solution. It can help quality of scans done, and also in general, I would say at the moment it's a big assistant to the radiologist, but not a replacement. Yeah. So there are also some limitations. For example, AI methods are very data dependent. They actually need a lot of annotation, so we need a lot of ground truth to be able to train them. And they have the problem of black box nature. They can lead to a significant ethical, legal, and governance problem if they do not work as they are supposed to. And finally, I would say, despite all of these limitations and challenges, still AI, data science are good chance for revolutionizing radiology and shaping the future of medical imaging differently. Thank you very much for your attention.
Thank you, Sepideh, for this very, very interesting talk. Are there already some questions? Yes, up there.
Hello, thank you for the presentation. It was really interesting, especially in terms of models to predict if the patients are suitable for the chemotherapy. And I was interested in, like, what type of data is fed for these models, how these models actually make the decisions, and actually in the field of medicine, because accuracy is very important. How accurate is these models right now in the medicine?
Yeah, basically it depends on the application. For example, we did it for both breast cancer and ovarian cancer. In the case of breast cancer, the data which is fed to the model is MRI data, so 3D data we have from MRI, different contrasts, and this is the input to the AI model. We could achieve, our group, we could achieve up to 95%, which is at the moment the level that is actually the group are actually delivering that. So 95 is already, I would say, perfect accuracy. However, in the case of ovarian cancer, the accuracy, the range is lower. It's around 70-something, 80-something. Therefore, as I showed, in the case of ovarian cancer, engineers came to the idea to integrate data because the accuracy only with imaging is not so high. Therefore, they are enriching the information space by bringing other type of data, for example, genomics, transcriptomics, clinical data, and so on, to increase this accuracy again to up to 90 or something like that. So it depends on the application. In the breast cancer, MRI image was enough to reach this high accuracy. For the ovarian cancer, at the moment we do not reach that accuracy. That's why we do data integration.
Thank you very much.
Yeah, sure.
Hello, thank you for the presentation. I'd like to add on the top of that question.
Yeah.
So how much is your precision?
You mean because of a data imbalance and so on?
I mean, because it's a medical data, so
Yeah.
particularly, I mean, maybe we are not interested in the accuracy.
Yeah.
Maybe we are interested in the precision.
Yeah, so we applied F-mean and we applied several other, specificity, I don't know, sensitivity, the precision. So they're all reported all in the range between 80 to 90%. So everything is high at the moment. And our data was kind of imbalanced data at the beginning, but recently we are just adding like more data because we want our model to be more generalized. So I would say the precision is also in the range, in the high range at the moment for the MRI, but not for the ovarian, actually, cancer.
Okay. So if you said like the limitation, we have a limitation with the dealing with the ground truth data.
Yeah.
And this might be affected your the model, like the precision thing. So how we are dealing with the situation?
For what?
For your precision and this labeling of data. You don't have a more ground truth of the data, right? So this is a limitation.
Yeah, at the moment what we do is that we are collecting more data from different centers to kind of make the model more generalizable, because if you just stick in one center data and you just stick in the ground truth from that center data, your model will not work when you apply new data from another center. We are working closely with different centers from Cambridge University, also inside Austria, and we are just trying to improve basically whatever the performance of the model is with external data.
Okay.
Yeah.
Okay. Thank you.
Yeah, sure.
Olivia had, okay.
Thank you for the presentation. It seems that the use of artificial intelligence in the field of medical imaging enjoys a higher acceptance, I think, than in other fields. And I would like to ask you that about the bias thema.
Yeah.
It is true that the bias problem not so strongly involved here is. So what can you tell us about the classification and prediction of patients, maybe?
So there are different types of bias. So one bias is when you stick in one single center data. So your data is biased with that specific center data, and this cannot be generalized as we already discussed. Another type of bias is gender aspect. So you only feed the model with, I don't know, when it is, well, in the case of breast and ovarian cancer, it's clear, but in the other type of cancers, when you feed it only with a specific, gender data. And the other thing is that when your data is not a fair representation, for example, you don't consider age, you don't consider the history of the patient inside the model, you don't consider all other aspects. So these are basically biased data, biased input data, which needs to be considered. At the moment, we are in the stage that we are not so much worrying about difference in age and, I don't know, history, but mainly worrying about collecting data from, different centers to make sure that this is generalizable. And we believe that we need to fine-tune at the end our model based on biased data, which could be kind of generalized for all other aspects that we mentioned. So basically, this should be part of development to kind of make the model robust toward these different bias aspects. Yeah.
Okay, over there are 2 more questions.
Yeah, please.
Thank you. Thank you for the very interesting presentation. I actually have 2 questions, because we were talking about the breast cancer and ovarian cancer, and what about the other cancers? How does it look like? Is it also in the work to get this far as with the breast cancer, as we already said? And another question, straightforward, is how broadly is it used in the Austrian medical healthcare? Do you work with all of the institutions or a lot of the institutions and share their data with you? Yeah. Or is it still in the works? They are maybe not that open to collaborate because of several data sharing, protection, and all of these topics that are very sensitive at the moment.
Yeah, thanks for a nice question. So answering your first question, basically AI and data science image analysis can be applied in any types of cancer with a high, I would say, performance. For example, in the case of lung cancer, which is also one of the very common cancer type in human in general, AI can help to detect all the lesion within the lung, and it can predict whether the patient would have cancer in future or not. But you see, just depends on the cancer type. The task is defined differently, right? So for the ovarian and breast cancer, chemotherapy, neoadjuvant chemotherapy is a common method. That's why it's important to predict that one. In the case of lung cancer, it's important to detect this lesion in advance and kind of predict it advance. Also, in the case of, for example, with the mammograph, it's important to detect it in advance. So it depends on the cancer type. We have different definition and different tasks. But answering your other question, at the moment, our center, because I'm from Danube Private University, we are at my university located in Lower Austria. At the moment, the focus is to get and collect data from Lower Austrian institution, which we have access to oncology information system of the whole Lower Austria, and now we are collecting from different centers, which is already a way of generalizing our methods. However, we are now getting data from even other countries and all over the Austria. I would say the data sharing protection, as you correctly mentioned, is over the bottleneck, because development model is one side, but getting access to that data is I would say, especially in the medical case, not everyone want to share the data. Yeah, this is another bottleneck. But now we are in parallel working in both sides, and we hope that we can get more and more data. Yeah.
Okay, I think one last question, then we need to go on.
Yeah.
Thank you so much. It was kind of a very moving presentation.
Thank you.
I'm someone which is like, or belong to this group of people who are very skeptical when it comes to AI and data. Yeah. Data usage concerning, many ethical aspects. But when it comes to medical issues, like it's completely the opposite, and you proved it today. Yeah. So thank you so much.
Thank you.
And I was especially moved regarding your research in prediction of treatment, as the other participants mentioned. Mm-hmm. You said that you're trying to use more diverse data in order to be more generalizing regarding your results. And so I would like to ask you, did you guys used to gather or come across data which considers patients' willingness and positivity towards their diseases?
Yeah.
And one last question, based on your so far knowledge, I would like to ask you, how high do you rate physicians' professions on the list of occupations being seriously threatened by AI and data science? Thank you so much.
Yeah. Thank you for the attractive question. So answering the first question, which was more about data protection, or let's say concerns of the patient to share the data. So we never can have access to data that the patient was not happy to share. So there is an ethical approval and the patient consents procedure before we get access to the data. If the patient says, for whatever personal reason, I don't want to share my data, we don't get access to that. However, in our group, there is also some researchers, profession working on the psychological aspects of using AI, basically in medicine. So we want to evaluate patient's attitude toward using AI. We want to evaluate the clinician attitude toward using the AI. And we want to really a little bit address those challenges, a little bit work toward making that, well, this is for improving next generation of medical technology. Of course, if we do not develop a data protection strategy, they would not be convinced. So we need to work in parallel in both aspects. First, the patient, the clinician should be happy, and then we should develop methods to convince them your data is safe. So we are working in both dimensions. I would say it's not easy. It's one of the difficult part of addressing that, but we are aware from the current challenges. Yeah?
Thank you. I think we are...
we can discuss
yeah.
more, yes.
Sepideh will be around the whole day.
Yes, I'm around. Yeah.
She's even there in the afternoon doing a workshop, so if you're interested.
Yeah, there is a workshop about medical image analysis. We explain basics of medical images. If you're interested, you of course can join.
Yeah, exactly, in the afternoon.
Yes.
Thanks a lot for your talk.
Thank you very much.